Hey everyone, I have the pleasure of presenting some joint work with 6 wonderful collaborators, all of them at Harvard. Sara, David, Ariel, Gili, Itai, and Manuel. And Gili, Ariel, and Sara are all in the room. So if you have any questions, don't just talk to me, talk to all of us. If you have hard questions, talk to them. Okay. Generative social choice is a design framework for social choice processes that are both AI enhanced and that allow to elect alternatives that are unforeseen, that maybe a priori we didn't know could even come out of this. And we have this whole general framework, and I'll touch on that all the way at the end of this talk. But just in the interest of time, I really want to focus in this talk on the specific instantiation of this framework that we have, which is in a setting that Daniel has already touched on, namely online participation platforms. So Daniel already mentioned one of these platforms that we have in mind, Polis. There's a similar platform called Remesh. Both of those have been applied in fancy settings. So Polis, for example, has been used by the government of Taiwan to inform them about what people wanted out of the regulation for Uber and Lyft. With Remesh, for example, have been used to inform, to gather what people in countries at war wanted out of a peace agreement and trying to push the generals towards peace. So very important stuff. Daniel has already shown you some screenshots from Polis. Those are just some more of them. Really, those platforms just allow you as a participant to share your opinions on a topic in a very deep manner. So you can write one or several statements, you can engage with the statements written by other people, and you're producing all this really valuable, deep, but unstructured, largely, information about what your preferences are. And then the big challenge faced by these platforms is how to make all of this information, potentially about tens of thousands of participants, legible to a decision maker who wants to base their decisions on what people want. And so Polis has some visualizations. Here, for example, you see some clustering and some 2D embedding of participants based on their preferences. This is only based on the voting preferences, not on what they write. But here, really, I want to focus on the second form that an output might have, which we call a slate of statements. So down here, you see one of these from Remesh. Slate of statements really just means there's a fixed number, a small number, maybe 5 or 10 statements, and you want to select a set of statements that give you a good idea of the overall distribution of preferences. And so far, this is done in a very heuristic manner. It's also done in a very limited manner, where these statements can only be statements that people have written. And our instantiation of our framework is really all about how to do this in a more rigorous and much more ambitious way. Okay, so what we want to build ultimately throughout this talk is an algorithm, which is a little machine, of course, that has an input and an output. The input are free-form expressions of opinions. So we have a range of participants, and for each of them, we just have text that describes in as much detail as possible what they think about the topic. So for example, in Polis, this could contain all the statements that they have written. This could contain where they voted yes or no on agreement with other statements, everything else that we could find. And then what we want to produce is the slate of statements. So there's some number K, just like in committee elections, this was mentioned earlier in the talk. So here, for example, 5. And then we want to produce the slate of 5 statements, and they should be represented. And one of the really big things here, and this is kind of like taking the challenge that Daniel has mentioned of having many candidates, we take this to an even larger extreme, right? We don't want to limit ourselves to any of the statements that people wrote, or that maybe we foresaw as good statements a priori. We want to somehow simulate doing social choice over the space of all possible textual statements that would make sense to put on the slate. And so implicitly, the set of candidates that we have available here is maybe infinite, or at least humongously large, way more than we can even show. We might have many more statements that we can choose than we have participants. And so this is really the challenge driving this. So we break down the design of this algorithm into 2 stages. In the first stage is really one that is a theory, a social choice theory. And specifically, we build a voting rule that has good axiomatic properties, with the wrinkle that because our task of working with a super large candidate space, because it is tricky, we will actually allow ourselves to use certain oracles. And then in the second stage, we'll implement these oracle queries. Okay, now let me first make some model. So we have a set of agents, very standard, and we have a set of statements. Think of those as the candidates or the alternatives, and think of that set as being humongously large. And then we have slate size K. Every agent in this case here has a cardinal utility. This is a bit of a deviation from some of the other settings. So we just assume that every agent I has some real number, ui alpha, for every statement alpha. more is better. And the job of our algorithm is to choose a multi-set of k-many statements. But because we don't get the statements, capital M, as part of our input, because we don't get the utilities as part of our input, instead we will navigate the space through some queries, which I'll define in a couple slides. But before I go to that, I first want to fix the objective that we actually want to achieve, the axiom that will define the representativeness in our setting. And for that, we're leaning on this literature that I don't think has come up a whole lot in this session, but came up, for example, yesterday, which is in the tradition of approval-based multi-winner elections. And this line of axioms called justified representation. There are many axioms here, many acronyms. We add one more to the mix because we think it's particularly well suited for the kind of summarization that we want to do. We call that balanced justified representation. So I'll walk you through what that means. Here we have the slate of statements that we want to find, k-many. And we want to find such a slate, and we want to find a balanced matching of the agents to the statements. So that just means that we match them up there, and we want to do that in such a way that every statement represents an equal number, an equal sized chunk of the population, up to maybe differences in rounding. And it should satisfy the following thing. There can't be any coalition of n over k agents. So in this case, n is the number of agents is 15. There are k equals 5 statements, so 3 is the number of coalition size that we worry about. There can't be any possible statement, and so these statements don't come from the slate. Those are statements that come from this humongously large set, capital M. There can't be a level of theta of satisfaction. Here, theta is mild approval, such that every agent likes the statement that they're matched to at most at theta, and likes this dreamt of statement, the yellow statement on the bottom left here, strictly more than theta. That's a sort of poor violation. This is unfair because these 3 agents are numerous enough to deserve one statement on the slate, just numerically. And they can come up with something that represents all of them much better than what they currently have. So this is what we want to rule out. Are there any questions about this axiom? Okay.
And it's strictly more than theta.
Strictly more than theta. And one important thing is here, you could imagine that it's enough for everybody just to strictly prefer the statement that they dream of relative to the one that they currently have. That's much more than, looks much more like a core stability. And unfortunately, we inherit impossibilities from, for example, like the classical multi-committee elections. So this is kind of the best approximation to that we can get. Okay, so the one thing that's still missing are these oracles. How can our voting rule have any chance of getting there if it doesn't even get the candidates in its space? And so we imagine that we find these beautiful black boxes wearing magic hats on the sidewalk, and they will be exactly what we need to build this voting rule. So the first black box is called the discriminative query, and it does something that is pretty straightforward. So into this black box, we can feed an agent I, and we can feed a statement alpha, and the black box will tell us how much this agent likes the statement alpha, so UI alpha. Then there's the second black box, which we call the generative query, which is even more magical. So it takes in not just a single agent, but a whole set, capital S, of agents, and it takes in this integer R. And this is what will allow us to find new statements in the space of all the statements. Namely, this black box will generate a new statement alpha, and namely a statement that has the property that the largest utility that any agent in S has for the statement is as high as it can be for any statement. Okay, that's a bit of a mouthful, but think of R in terms of the extremes, right? R might be the cardinality of S, in which case what we're maximizing here is the minimum utility in S. So then we have a maximum objective. And so what the generative query would be giving us is a sort of lowest common denominator. And at the other extreme, if R is 1, say, then what we're trying to find here is just a statement that some agent likes as much as possible, but we don't care about whether other people like it. So R is this kind of rank parameter that allows us to interpolate between really high specificity and a lowest common denominator, and we'll need both of these extremes. We need to be able to get the middle point that we really need for our algorithm. And so based on that, we implement an algorithm that is actually fairly classical. You could call it a greedy egalitarian Monroe algorithm. It works like that. So we start with all the agents here on the left, and we feed them into a generative query as the set of agents. And then R we set exactly to n divided by k, which in this case is 3. The generative query will produce for us a statement. It's a blue statement here. And we now use a discriminative query to figure out exactly how much each of these agents likes the statement. And then we take the 3 agents, the N over K agents, will like the statement the most, and we'll move the statement into the slate. We'll move these 3 agents, we'll match them to the statement, and then we recurse with the remaining agents. So we feed those into the generative query with the same R, we get a new statement, we use the discriminative query to figure out who to match, we have a new statement to add until we ultimately complete the slate. And now, using an argument that again is very similar to all these greedy algorithms in the multi-winner elections literature, we can show that this greedy voting rule using our queries satisfies balanced justified representation. In our paper, we also have additional theoretical results where we consider the case that maybe actually we can't feed arbitrarily large sets of agents into the generative query. This might be motivated, for example, if the context window of these LLMs is not that large. Since we've started writing this paper, the context windows have really grown in size, but it's still really not clear that the LLM really can reason over really large inputs. So you might want to focus on smaller sets of agents, and this is actually something we see in practice. And so we have some math telling you in which cases you can or you cannot still achieve BJR. And I want to leave the theory at this. And I want to use the remaining few minutes to actually tell you about how we implement these queries to actually produce an algorithm that can be run in practice, how we ran it in the real world, and I want to zoom out into the more general grid. Okay, let's implement these queries. So the discriminative query, to recall, right, it takes in an agent and a statement and gives us back the utility. So now we're turning this from a magical procedure into an AI procedure. We're implementing something real. We're feeding in this textual description of the agent, we're feeding in the statement, and then we're predicting some utility level. I don't want to talk too much about the details here of implementation. Very happy to talk about this, but we implement this using the GPT-4 base model. And the important part of the validation to take away here is this plot here. And I'm cheating a little bit because I'm not yet telling you what data we're evaluating this on. This is the data that we gathered in our real world deployment. You'll hear about it in a couple of minutes, but this is a data set where we asked people to rate their agreement with different statements. And so on the y-axis, you see the statement, the rating that they really gave between 0, very low agreement, and 4, very high agreement. And on the x-axis, you can see what our implementation predicts. And while this is not perfect, if you squint, the really important pattern here is that there's a strong diagonal. And that means that we're recovering a lot of the signal, extrapolating people's preferences based on the text that they gave us, based on the ratings that they gave us on other statements to new statements. So we feel pretty confident with that. The generative query is the by far trickier one. It's much harder to implement. It's much harder to validate, right? We have a set of agents. Really, we want to get the statement alpha that has the highest alpha largest utility out of all the statements. That's a really high, really tall order. We tried, but we don't think we can implement this using a single call to the LLM. Instead, we have an ensemble approach where we have different approaches that all try to generate statements. We score them based on the discriminative query relative to this objective, and then we take the best one. And so far, our evaluation mainly shows that this ensemble approach really does make a difference. So if we look at different relatively weak ways of generating statements, we can see that we really profit from taking the best out of these, because even though each of these generation sources sometimes fails, they seem to fail in not so correlated manners. And so it's likely that even if you have a few and you always take the best, there always is a best one. And so while I can't explain the whole graph, the important part here to take away from is that the maximum column is higher. So the alpha largest utility in this experiment is much higher if we take the maximum, if we take any individual approach. Okay. We have not just academically written a paper about this, but we've actually run this in practice. And in part, we've done this because we were part of a program by OpenAI on democratic inputs to AI. And we received money from them in exchange for also promising to run this in practice for a question that they care about. The question that they care about, in this case being, to what extent chatbots should be personalized to the user. There's also maybe a funny thing. So back in November, this was a purely hypothetical question. At this point, ChatGPT has a memory function, and so some of that personalization has actually happened. In November, it was all post-chances. I had no idea that this was coming so soon. And we run our process as follows. So we use the platform Prolific to recruit a sample of 100 representative US residents, representative according to age, gender, and race. We force them through a really in-depth survey, trying to tease out their preferences on chatbot personalization. And then we use exactly this process that I've described. So this greedy egalitarian Monroe process together with our implementation of the queries to extract the slate of k equals 5 statements. There are many ways in which we validate and analyze the slate, of course, but I don't have so much time. So one evaluation I want to quickly show you is that we just generate, recruit an entirely new sample of residents. And we ask them to rate all of these statements on the slate. And then we do a matching where we try to, in a balanced way, match people to statements so that they're as happy as possible with their matched statement. And the happiness for the statement that they're matched to is then a measure of how well the slate really represents the distribution of preferences in the population. And the tagline figure here is that 75% of our participants feel perfectly represented by the statement that we matched them to, and 93 at least feel mostly represented. Very happy with all of this. But one thing that I want to just briefly say is that we think that this challenge that we're solving here, namely wanting to do social choice theory, where the alternatives can be things that we don't know a priori, seems like a very general thing, right? So, for example, if a legislature is deciding on what bill they should enact together, right now they're voting yes or no, but in the voting process itself, there's nothing that can amend. So we have all these external procedures. It would be really nice to have proportionality guarantees over the process as a whole. Or if your faculty senate is voting on something that, for example, produces a policy or produces text, it would be really nice to be able to do social choice in these open-ended contexts. Or if you're in Brexit, it would be really nice if there had been options other than Brexit and no Brexit that could have come out. So it's a very general phenomenon. And we think that this might be a very fruitful direction to more broadly beyond this one single individual example. And this way that we've broken down the design of this process. So first, define Oracle queries that are useful, do some theory, show that if these Oracle queries do their job, we can satisfy these axiomatic guarantees, and then try to implement and validate these queries in the real world. That this is a very promising way to build good processes. I want to conclude here with a take-home message. So in my mind, these capabilities of large language models are incredibly attractive, and attractive to the point where I think we don't really have a choice in whether they will be used for many practical contexts, including online participation in the future. Right? So for example, they allow people to communicate in natural language their preferences, which is so close to how people can actually communicate, how they actually think about their preferences. It's making things much more open and approachable. So it's really, really powerful. And I think people will use it. And we're seeing a lot of examples in the last year of people putting them into prototypes for participation platforms. But the danger with that is that our classical social choice techniques, our proof-based techniques, don't completely extend to these large language models. And so there's a real danger that people will start building these janky constructions here that aren't really robust, that aren't really fair, that aren't really democratic. And I think we as a field should try to find an answer to that. And generative social choice is just one possible vision, but it's one possible vision for how the things that we've built up as a field, our mathematics can guide the design of systems that themselves are not entirely captured by mathematical guarantees.